So here we have just some more examples of using normal CDF. And so rather than going through every one with you in all detail, I'm just going to do some highlights here to summarize what we've done, and we can move forward. So the first question here, looking for the area under the standard normal curve z-scores, standard normal to the left of a number. So probability z is less than a value. So just writing down the location there and knowing that if we're looking for area to the left, that the order is lower bound, upper bound. So negative infinity to that number. So lower bound, upper bound are always left to right. And then the other thing I added to this picture, just as a reminder, is that it's good to have a feel for if we're shading more than half our picture or less than half our picture. So I drew this line down the center and just indicated here that all of this area to the left would be 50% of the picture, or in decimal 0.5, and all the area to the right of center, 50% of the picture, or in decimal 0.5. So this area that I was looking for, I knew was going to be smaller than 0.5 because it's definitely shading less than half that picture. And this answer confirmed that it was less than 0.5, it was 0.0384. So that was just some additional information there. And then another question with normal CDF, now looking for area to the right of a z-score. So once you know where your z-score is, shading to the right is probability of z being greater than that number. And anytime we're shading to the right, our order will be starting at the value and then going out to infinity for our upper bound. So our value out to infinity. So the thing to always just keep in mind here is when you have shading to the right, the upper bound is infinity. When you have shading to the left, the lower bound is the negative infinity. All right, and then I did one here with shading between two values. So for this one, you'll notice that my z-score between the two values are actually given to 3 decimal places. So I know I've been doing 2 decimal places a lot for z-scores, but there's no rule that it has to be 2 decimal places. We just happen to do that quite frequently. Also 3 decimal places can be common. So I just wanted to do one here that'll come up later in the semester as well. So looking for the probability of getting a z-score between 2 values. So in that case, we don't have to deal with infinities at all. We just have a lower bound and an upper bound. And in this case, because it's the same value but negative positive, we could think of that as the middle portion of the graph. And if you want to check that one out and enter it, that will end up being 90% of the graph. So the middle 90%. And I did one last one. 1.96 is a z-score that will come up a lot this semester. And this one is the probability that z is greater than 1.96. So again, always good just to do even a by hand quick little sketch, just to get a feel for these graphs that we use a lot this semester. And then looking at the probability z-score is greater. So this little area here past 1.96. And again, shading to the right is lower bound, upper bound. And then you could check that one out. So if you want to try those on your own, that covers all the cases of using normal CDF to find a probability or an area. And then our next task is going to be going what I call in reverse. So in reverse, meaning what if instead of being given z-scores that we are graphing here, what if we want to find z-score? So let's take a look at our next bit here. So this function called inverse norm on our calculator will allow us to find z-scores. So let me set this example up. It says find the z-score that separates the top 10% of z-scores from the rest. So Now we're on something new. It doesn't say find area. It doesn't say find probability. It says find a z-score. So I'm going to come over and zoom in on this picture. So we're talking about z-scores. We know that the mean is 0. And I haven't put any z values on this number line because we don't know where our answer is yet. And we don't have to have everything drawn to scale. We just need to know location-wise, where is the top of the graph? So the top 10% of z-scores. So top would be the values to the right. So this would be the top of the graph. This would be the bottom of the graph. So top is to the positive side, and we're looking for the z-score that separates the top 10%. So remember, the whole graph is 100%. So top 10%, there's going to be some value. I'll put a question mark there. I want to find that missing z-score that separates 10% of z-scores, the top 10%. So we'll be drawing this picture quite a bit. The top 10% means that the area to the right of that unknown z-score needs to be 10% of z-scores. So area is 10%, or in decimal 0.10. So that's the question. So this picture defines the question. What is the z-score? All right, so the question, how do I find an unknown z-score? The answer is, if you know the area left of the z-score, we can use this function inverse norm. But the requirement is it requires us to know the area to the left of the z-score, and we don't know that. We know that we're looking for a z-score, and the top to the right of it is 10%, but we haven't gotten any information yet about left of it. So we discussed this previously, that every z-score is going to separate the graph into two parts, the part to its left and the part to its right. So the area to the left and the area to the right together would have to equal 1, or 100%. So basically, I'm going to just step through given information. So if we're looking for a z-score and it separates the top 10% from the rest, that means that the area to the right of it is 10%. But we need to know the area to the left of it in order to use our inverse norm function. So the area to the left and the area to the right add up to 1, so they're complements. So area left, the rule of complements would say it's 1 minus the area to the right of that z-score. So in decimal, if we take 1 and subtract 0.10, that will leave us with 0.90. So we probably could have done this in our heads in percent version for sure. If 10% of the graph is to the right of it, then the other 90%, of course, would be to the left of it. So we're just trying to get used to working in decimal more often than in percent. But they are complements. So 90% plus 10% is 100%, or decimal 0.9 plus 0.1 is equal to 1. All right, so that's the key. So somehow, in order to move forward, you're going to need to find the area to the left of the z-score. So what if you don't know it? Well, then you have to find it. And that wasn't that hard. So if you know the area to the right, that's the rule of complements for the area to the left. And then the calculator can do the work for us. So that missing z-score, we find it by using the inverse norm function. And I'm going to just abbreviate it inverse n for inverse normal. So we got our normal distribution, this inverse function. The input says for this z-score, it wants to know the area not to the right of it, but to the left of it. And now we know that 0.90. And then we need to include the mean and the standard deviation for the population. So in this case, again, working with z-scores, the mean would be 0, standard normal, the mean is 0, and the standard deviation is 1. So the mu and the sigma for z-scores, standard, normal, the 0 and the 1 are the default, just like they were with normal CDF. So we can shorten what we write here and actually just say 0.90. If we leave off the mu and the sigma, it will assume we mean 0, 1. So if we weren't working with z-scores and we were working with churros again, like calories in a churro, well, then we would have to put in the appropriate mean and standard deviation. All right. So there you go. That's how you find a z-score. So if you know the area to the left of it, inverse norm, we put in that area to the left of it. And then on our calculators, when you go to your distributions, you'll see your inverse norm below your normal CDF. And we put in our 0.9, the area left. And I'm going to be rounding our z-scores to 2 decimal places, occasionally 3, but here I'll do 2. As always, just follow rounding directions if you're doing problems online. In this section, sometimes they ask for 4 decimal places, but we'll stick with 2, and I'll say that answer is a z-score of 1.28. So I can now tell you that z-score, I'm going to put the answer over here, a z-score of 1.28 separates the graph into 2 parts. 10% of the graph is to the right and 90% of the graph is to the left. All right, and then we'll just have to take a look at various cases of applying this. But the key is when you read a question, we know we're talking about using inverse normal because we're looking for a missing z-score.